Lourenço, who's going to tell us about the p-adic theory of local models. So take it away.
Thank you. Okay, so right. I was trying to share my screen. Okay, now it works. Very well. Okay. Right. I'd like to start by thanking the organizers for inviting me to the symposium. Okay, so in this talk, I'll focus on two different papers, HLR and FHLR. The first one is joined with Anschutz, Listen, and Bischoff, and is concerned with proving the Schultz of Einstein conjecture, namely that there exist unique local models that represent certain portions of the BDR plus Grassmannian. In the integral sense, just like Affine introduced in the previous talk. So the first article uses perfectoid methods a lot, but we'll also need to mention at certain points the second one, which Fakhdin, Haynes, and Bischoff, which goes about constructing the explicit objects that we'll use to prove the conjecture, and then also say something about the singularities. And the main contribution in a way, so the second article uses older techniques, but we try to also treat wildly ramified cases at the same time as tamely ramified ones, which was something that wasn't so well understood in literature. Okay, so let me just fix some notation. I'll be working with a connected reductive QP group and the parahoric ZP model for G. S will be maximal split torus over QP brevo, centralizer T, and B will be a Borel subgroup over QP brevo. I mean, these two last data are not really, so they're not really necessary, but they're helpful to explain something later on. Also fix a minuscule co-weight dominant with respect to this choice of Borel. I mean, this is a geometric co-weight, so defined over TP or TPY if you prefer. But and then I'll take some special conjugates over the relative value defined over QP level, which I'll call lambda. This is a certain orbit that was already introduced by Kotlitz and Kapitov, I believe. And then E will be the reflex field of that orbit, which has a certain Resi field FQ. Okay. And so let me try to explain what these local models are about. So some motivation, historically, they appeared via a map of this sort from S to the quotient stack of M-log mod G on the left. Should be a smooth map of relative dimension equal to that of G. And this is more or less equivalent to some sort of diagram of this sort, where the map on the left is smooth and the one on the right is the G torsion. They have the same dimension, which in particular implies that strictly Zelian local rings are isomorphic. And this basically tells you that once you control the singularities of this object M-log, then you also control the singularities of this calligraphic S, which I didn't tell you what it was, but as the letter may suggest, it has to do with Shimura varieties. So usually, I mean, initially local models appeared related to the theory of Shimura varieties and trying to understand certain their reduction, their arithmetic. I mean, this goes back to already to work with the linear Rapaport, linear Papas, and many more names. But I also wanted to mention that recently there's been tremendous progress in understanding how canonical the canonicity of the integral model is, especially in the work of Kisin Papas and now very recent preprint Papas Rapaport. But the first time, for instance, local models were studied systematically was in the book of Rapaport Sync, which studied moduli of divisible groups, which were represented by certain formal schemes, and they use these local models to control the formal scheme at the local level. And also, something that is worth mentioning, if you leave the p-adic world and you work over in equicharacteristic P, such as, for instance, in Feng talk yesterday, you get a moduli of Stukas in characteristic P, and you also get a local model diagram just in this way. And I guess the people who've studied, so this appears in work of several people in geometric representation theory, but I think the singularities part is, if I'm not mistaken, this has appeared more often in work of Aft and some of the students, which I mentioned here. But beyond controlling the singularities of arithmetic models of Shimura varieties, local models can also be used to, for instance, understand nearby cycles of those calligraphic S's, and this has led to, for instance, progress in the Haynes-Cottbus conjecture on test functions by Haynes and Richard. And also, there was also recent progress on counting mod P points of Shimura varieties by João and Van Hoften. And finally, maybe the most surprising and actually alien to this talk application that there is to the study of p-adic representations. I won't be discussing this, but I guess it's interesting to know these type of techniques are also useful there. And so to more information, I guess you should check this work by Lille, Levin, and Morra. Okay. So now I'll turn to the theory of local models themselves, and I'll ignore, the p-adic Stuka side for most of the talk. Just focus on the Affine Grassmannians, essentially. But for me, there are essentially three ways of approaching the theory. So the first one, the more elementary that appeared, was based on moduli problems. The main works, I think, were given are due to Papas, Rapaport, and Sync in several instances. So the idea is that the same way Shimura varieties are moduli, principally polarized abelian varieties, and you use this interpretation to define their reduction in lots of cases. You can try to do the same using just linear algebraic data of this sort, like some locally free quotients of some object here that is what is called a periodic lattice chain. It's a chain of lattices that repeats itself and lies in a certain vector space. So this makes sense, for instance, for PL Shimura varieties. And so this type of data is related to G, and this should also be subjected to some Cottbus conditions. So for instance, the rank of those locally free quotients Q should be fixed, and there's still extra structures that I won't mention, but it relates somehow to the co-weight mu. This, as I said, this is a very concrete description, and in a way, it gives you some sort of finite Grassmannian extra structures. So you could, so it looks very nice. The main issue at the time was that it wasn't really possible to prove as many geometric results about these objects as one could hope for. I mean, later on, they were even called naive models instead of local models, at least some of them. And the problem was that if you just write the minimal conditions already, Papa's noticed that flatness is not a given, so it could fail. And then you'd have to add more conditions, and it was a complicated problem to determine how much was needed actually. And so then another approach appeared, slightly more sophisticated, which allowed to understand the geometry better, which was to use this affine Grassmannian, which is some sort of infinite dimensional space. It's actually, I mean, it's an instance, in this case, parameterizing some torsors over this formal disk using power series, and then with a trivialization over the function. Okay, and so you could try to find your local model, or at least a special fiber inside there. Something that was done by several people listed here, like Guts, Falting, Papa's rule 11. And then you use techniques from geometric representation theory to get a grip on what was happening with these objects. Okay. The issue this time, I mean, I think it was something that perhaps annoyed Schultz a bit, is that you'd have to do some choices, right? Because this looks ill-defined, because what is G prime? I was saying with G, and what is G prime? This is a parallel group scheme, but over FP power series P. And what is the relation between this and mixed characteristics? So it's not very clear. The problem is that these power series are an equicharacteristic device. Okay, so you get certain objects, and you know a lot about them. So these works that I mentioned were tremendous at the time, and they're still now. But it was not totally functorial, and so this was not a good foundation for a theory, and that's where Schultz came in. In his book with Weinstein, he proposed that we should look at some closed subsheaf of this one, so where of a different affine Grassmannian, where you use the RAM theory range. Okay, and I mean, this is very nice in the sense that it sounds like a good theory. It doesn't depend on choices anymore. So I mean, if you want to do algebraic geometry, you're a bit limited. Indeed, this is not going to be representative, but yeah. So the idea in our talk is to explain how to reunite all the second and third approaches to two different types of affine Grassmannian. I just wanted to mention that there's work of João and Bad Schultz that is also important to this, because it's some sort of specialization of the big RAM Grassmannian. You know, you get the Witt flag variety, and they did foundational work on that, which we're going to use, as we'll see later on. Okay, but I guess beyond the several types of approaches, let me just say how the local model should look like abstractly, not using any PEL type interpretation. Like, you should have functions with flat projective schemes endowed with a GOE action, and you should be able to say something about it. At least the fibers you should be able to describe. The generic fiber should be this classical like variety. The special fiber should be some finite type scheme, reduced indeed, which I denote by this sort of a canonical new admissible locus. It sort of appeared already, it goes back to Kottwitz and Rapoport, because they looked at this set over here, this combinatorial set. At the time, this did not have enough structure, but I mean, it relates to the Witt flag variety, So I'll explain in a few slides how this corresponds to some perfect scheme, and then there's a way to canonically be perfected, like that. There's an optimal deperfection that I think already appears in that paper review I mentioned. And so I mean, that's what the special fiber should be. Then to connect them, I can't really say everything right now, but at least you should have some sort of open smooth locus, which consists of a union of orbits, which are supposed to be glued in some obvious sense, which I'll list to you, and whose special fiber is still dense. Yeah, this object might look innocuous, but it's actually going to turn out to be important. And the joint goal of the two papers is basically to construct such an object that represents a closed subsheaf of the GRG-OE. And I know this is getting into a very long introduction, but before continuing, I just like to mention the equicharacteristic case, because there it's very easy to construct a local model because you have an affine Grassmannian that is an in scheme. Like you use two different variables, T and R, one that relates to the parahoric group G over FPT, and the other to the coefficients R. And this defines you an in scheme over FP power series R, which deforms between the constant Grassmannian on generic fiber and the affine flag variety and the special fiber. And so here you get an in scheme, so you can define M block as some weakly normal flat closure of FG mu inside GRG OE. Weakly normal means some sort of normalization with the same topological space. And it's needed because of AGLR. It's a paper I've written with Haynes and Fischaltz, where we explain that for some bad primes, there are Schumacher varieties which are not normal, unfortunately. Yeah. Okay, so now we know what M-log should be in equicharacteristic. So you just have to study the singularities, and what you get is that under a mild assumption, which I'll ignore for a moment, you know that this guy is normal, Cohen-Macaulay, which allows you to do commutative algebra on it. You also have this pseudo-rational property, which gives a lot of homological vanishing. It also satisfies those desiderata that I had imposed in the previous slide. So you know what the special fiber is. You also know that you have that nice smooth open locus. In particular, the special fiber is also pretty well behaved from a geometric point of view. So it's going to be F split, which means that this canonical morphism in characteristic P splits in the category of OX modules, and compatibly so with all the reduced subschemes stable under G. Right, and yeah, I guess F splitness gives you mild singularities, like locally, but also globally. Again, it tells you that certain homology groups of line bundles vanish, and that's pretty good as well. Okay, so actually I should say that a result like this was known for, as I said, I guess at a certain point already, for restriction of scalars of plane groups. So this relates to the work of those other authors like Falting, Slapopov, João, and so on, which proves several parts of this results. But what we do is we do it for almost all groups. Just a mild assumption, which I'll explain. The technique is, the main tool is that you need to lift your parahoric group scheme to some sort of analog over this two-dimensional ring that P breve power series T. And we can't really do this when p is equal to 2, we need to avoid all the unitary groups. That's the only assumption that we need. This has to do with the fact that just all the unitary groups are the only ones with reduced root system, non-reduced relative roots. And then it becomes complicated to make the construction work when p is equal to 2. That's the only issue we have. For all other, there are several families of wildly ramified groups for which this result is new. So, and we do it in new form. Right. Okay. So now we move to perfectoid stuff. And I need to start by V-sheaves, by explaining some basic stuff on V-sheaves. The first thing is how to pass from schemes to V-sheaves. Perhaps this hasn't been explained so in the literature, but there are two possible functors. You can take R plus valued points, or you can take R valued points. This leads to some quite different objects. One is quasi-complex, for instance. The other is not, only partially proper. So that, for instance, if you take the affine line in the scheme theoretic sense, then, the small one equals B1, and the large one is just the affine line as a V-sheaf. So there's a big difference between these two types of functors generally, but they coincide if X is proper, which is already, it's going to be pretty good for us. For instance, we'll use the smaller one to get specializations, and the bigger one is more useful, for instance, to study the derived category because of techniques such as hyperbolic normalization. Okay, and one result that one can show is that for proper flats, AWN, which is in the flat case, just means the same as weakly normal. Yeah, so I mean, it's some universal scheme with the same underlying topological space. Then the V-sheaf functor to V-sheaves over SPDZP is actually fully faithful. Okay, and right, so this means this functor captures all the topological information in a way. And the main thing that you use there is knowing that this triple functor is fully faithful as well, just for on the level of proper flats AWN schemes. So I mean, if you record the two fibers and the specialization between them, you can actually recover the scheme. It's just by, you pass through formal schemes and then you take global sections of power bonded elements, and this works. Okay. Right, and so the previous slide tells us how to recover the local model from its V-sheaf, but we need something else, namely, we need this theory of Kimberlitz due to Ian Gleason, one of our co-authors. I mean, these are some sort of integral models of diamonds. If you're into geology, you might understand the joke behind the name. Right. So, I also wanted to say that when we began the project, Ian was not involved, and so we were stuck for quite a while until we learned about his thesis, and then it was crystal clear that we actually needed this stuff to progress. Right, so let me explain what it is. So we introduced this notion of a proper flat rich p-adic Kimberlitz, which is some proper V-sheaf X over SPDZP, which is covered by integral perfectoids coming from a QP perfectoid, whose generic fiber is a spatial diamond with density points in the constructible topology, which then also prolong to uniquely to OP value points as per the sort of algebraic evaluative criterion, which is different, beware, from the p-adic one. The special fiber is representable by a proper perfect FP scheme known as the reduction. And then you also have a surjective quotient map. Maybe one of the most important things is that at last you are able to construct this map from the underlying topological space of the generic fiber to that of its reduction. And notice that this topological space is not equal to that of the special fiber, because the right side contains a lot more analytic ones, okay, which are not seen of bubble schemes. This is some weird phenomenon that, you know, it's a nuisance, but Ian took care of it for us, and you see this, we can't ignore it in a way. And the result that we get is that the same triple functor that was fully faithful in the scheme case is also fully faithful for these proper flat rich p-adic elements. And that came as a surprise to me. I think even to Schultz, this works. The proof is not very hard indeed, but once you just use the graph, it's just, I guess the difficulty is in setting out, looking for the right properties so that this works. So the definition of these special Kimberleys is where the merit lies. Okay, so now that we're done with the foundations of the sheaves, I can move to the geometric objects that we're interested in, like the affine Grassmannians. I'll start by the special fiber, okay, because it only involves perfect geometry. So this is a mean proper perfect scheme, which represents, so remember that she's hard always during this talk. It represents this old moduli problem on perfect algebras. This was introduced by João and then proved to be representable by Schultz. So yeah, once you have this, you can define your Schubach varieties, FLGW, which are closures of these orbits. And then they meet themselves some Demassier resolutions, which are just some twisted products of the same type of Schubach varieties associated to simple reflections. The simple reflections that appear in the words to which the Demassier variety is associated. Now, using this, we can introduce the mu-admissible locus. Remember that this was a combinatorial notion due to Kotlitz and Hapopov. So now it becomes a perfect scheme in the p-adic case. And then what I claim is that you can find some perfection. This is going to be a finite type scheme, still with an action of G FQ, because mu is assumed to minuscule, and it's the maximal such one. So this exists, and what we can show about this object is that under the same Mold assumption as before, it is Cohen-Macaulay. It satisfies the coherence theorem of João. This relates to some dimensions of global sections of ample line bundles, and it's also F-split compatibly with reduced subschemes stable under G. So, I mean, this is the same that I was discussing and explaining in equicharacteristics. So our proof is basically by reduction to that case via similar types of lifts, but this time it's along T maps to P to the uniformizer. We want to move from this two-dimensional ring to the p-adic case. And So then you can compare this to some equicharacteristic group, which is a reduction mod P of the set P by the power series T. And this gives you a way to compare the Demazio resolutions of the shoebox varieties contained in the admissible locus. If you go deeper inside the affine flag variety, this will not hold. So it's important that it's bounded in a certain way. But you can do that. Then you recover the shoebox varieties by line bundles, which are known. We know how they look like due to Rejo, which they computed the Pikachu. So the line bundles give you some sort of Stein factorization of the Demazio resolution. So they tell you exactly which fibers to contract. And so using then some geoequivariance, you see that these comparisons are actually unique. And so you can glue to the admissible locus and then you can deperfect. So you get an isomorphism, you get the theorem almost for free. In the p-adic case. Okay, so now back to the PDR plus affine Grassmannian. We know what the definition is. I mean, I guess in Affine fault, this was defined only in the generic fiber. Okay, and now we take the whole structure over SPDZP for at parametric level, and what we get is an int proper p-adic Kimberlite by work of this follows by Anschutz, also Schultz of Einstein and Gleason series. Just for a reality check, let us observe that over E, you get the diamond associated to what do you expect the generic fiber to be. And over FQ, you get already, because you know that part is the entirety of it is representable by the bit fiber, right? And you already have the admissible locus in there. So this looks pretty good. And you define the local model as a closure of FG mu inside this PRG OE. What you can show about this is that it is indeed the proper flat pitch p-adic Kimberlite that is stable under the action of GOE. So the action of GOE here is really important for us to get control on the topological space. I mean, without it, we wouldn't be able to. So there's no like underlying abstract theorem that we could demonstrate. And in general, it might be tricky to control the topological space of the closure. But in this case, we're sort of saved because there's an important thing that this V sheaf, the big one attached to G, is actually partially proper. That's helpful for us because of an anomaly of adic spaces is closed. Sub-adic spaces are immediately generalizable. This is something weird that doesn't happen for schemes, so you need to be careful when computing closures. But you still managed to prove this result. I think an avatar of this was used already in that preprint of Papa's AlphaPop that I mentioned. Yeah. Because they need the G action probably, and also the fact that it's flat. Right. Okay, so here I'll just explain what the main results on the geometry of these guys. What are the main results that we have on geometry of these guys? So the first one is that we determine what the special fiber of MGMU looks like. This will be done the next 2 slides. Actually, this also makes sense for mu non-minuscule, but I won't discuss this because I don't really want to. You need to work with the derived Tal category. So we'll be building on Fach-Schultz. That was also something that kept us stuck for a while. And the second result for the last 3 slides is that basically the Schultz-Weinstein conjecture up to some caveats. Namely, we show that the species is representable by an AWM flat projective scheme with GOE action to column lock. And under a very mild assumption, it satisfies the desiderata, which means that the special fiber is the right one. So the special fiber should be A can G mu. And the only problems that we have are, again, like when p is equal to 2, no odd unitary group, because of that construction of the lift that fails. And when p is equal to 3, we also need to exclude trialities. Sorry about this. I'm not sure if anyone's going to be heard about that. But there's a problem with controlling certain Galois automorphisms. So yeah, it's unfortunate, but we also can't really understand the special fiber in that case. Right. In any case, this will be done in the last segment of the talk. Okay. So on the derived talk category. So, you know, this is basically, we had to refact Schultz and improve a bit on what they did, because they only did it for reductive group schemes, right? We need to do it for general parahoric play. Also because local models for reductive group schemes are quite simple, as you might see. Right, so we have this category, the et al., which was already introduced in that paper of Schultz, homology of diamonds, and then studied further by Bach Schultz. We know after, you know, Laurent Bach's talk that it has a following structure. So you know that there's a notion of universal local cyclicity that works for these guys, which involves overconvergency, some Vernier dualizability. You also have a notion of perversity using some bounds on the dimensions of each strata in each fiber. Beware, however, that there's no such general notion of perversity for V-sheaves. So this is something quite specific to the Affine Grassmannian or in the respective stack, which perhaps I forgot to mention, but I mean, recall that this is just a quotient of GRG by L plus G, where L plus G is the group of automorphisms of the trivial torsor on BDR plus. And right, so the next thing we also have in this case is these constant terms, CTP, for some dynamic subgroups defined over that p-adic. This means attractors for certain coeds. And this gives you a morphism from GRG to GRG0. These are maps that, you know, they come from this technique of GM actions and then the corresponding hyperbolic localization. They have lots of symmetries, so they commute with a bunch of functors, and that's the only reason why we can actually control this et al. I mean, this was also already the case in Bach-Schultz, so that they could construct the Sataka equivalence for flat perverse ULA sheaves, basically by exploiting the constant terms. And well, this also holds true for the previous work, but in geometric representation too. Right, and okay, so one thing that we need to prove at first is this very crucial lemma in Bach-Schultz, so that you need to know that your family of constant terms detects whether an object is zero. And in Bach-Schultz, you just need one Borel, because basically once you have a stratum in the affine Grassmannian, you always have a dominant point, just like you have an anti-dominant point. But at URI level for us, this is not true. Most of the times you only have one point, you only have one point per stratum. And so you need to keep changing your Borel, basically. But if you do that, you can show this lemma. And so you can use it to to detect ULA property. The proof is the same as in Bach-Schultz. You just show that by rechoosing the Borel in a smart way, you can get at the intersection of the semi-infinite orbit attached to W with its Schubert's variety is just W. And so you can basically induct to understand universal locally acyclic objects. Okay, and this has a consequence on integral extensions. So you have an obvious integral extension map that's canonical. That there's no work there, but because of the way the CT maps are constructed and their very good properties, they commute with this integral extension, which is nice. And so if you combine this with what you know in the generic fiber already, then you see that you get an equivalence on ULA objects. So this is similar to recent work of Hans and Schulze on that prove this for schemes, and also they add some similar stuff on perversity, because this holds for nearby cycles for schemes, but it's not really known for V-sheet. So so this doesn't quite work in this case, because, well, the main issue that we have is some lack of parity. We can't really test perversity with the CTEDs, because basically the dimensional strata, and like for the Affine Grassmannians, that are contained in the same connected component, they're not all of the same the parity. And so that's an issue. We can't really define degrees after which we shift CTV, and then this preserves perversity. That doesn't really work. But another thing that the integral extension should preserve should be centrality. So I think we're working on this, but this should lead to another proof of the Haynes-Kottwitz conjecture on the semi-simple terms and the test function and so on and so forth. Which also, I mean, it would be new for some very few cases, local models which weren't available when Haynes and Fischhout wrote their paper, but especially also in the non-minuscule case, these weird V-sheet would also apply, I guess, which is something interesting to know. And finally, as a bonus, you get what the special fiber of the local model is. I guess that was the whole point of this detour, because you can compute the supports of the integral extension of this Atake object. And I mean, on the special fiber, if you analyze CT carefully, you get the admissible locus. But you also, by a density argument, you also get the actual special fiber. So they must coincide. That's quite nice. Right. Okay, so now I'll explain the idea behind representability. Okay, so here we're using, so our basic thought was that we need to connect the two fibers in some way. So maybe it's good. I mean, the more regular they are, the better it is. So why not try to resolve them partially? Okay, so we use convolution for that, obviously. So we fix the sequence U1 to UN of this minuscule dominant co-weights, and say that their supports are pairwise disjoint. This is important because you want like the sum to still be minuscule, because you want your object to have for instance, at least a representable generic fiber. Okay, so then you can define again a proper flat rich p-adic Kimberlitz just by composing these boundedness conditions, right? And you get this convoluted object with representable fibers by the obvious guys. I mean, the twisted product in the generic fiber splits. And in the special fiber, it's a bit more complicated, but I mean, I guess you have the Himazir revolution. You can, I mean, for such twisted product, you always have some type of minimal expression in terms of torsors under some groups. Yeah, which we keep choosing inductively. And what we can understand about these torsors. So I mean, it's not a much better problem than understanding the local model itself. The point is, we add this third part, which we said we should understand relatively well. And so we get a torsor over the third part. So the third part was this open union of orbits, right? And so now you get a torsor over that semi-orbit under G. And basically what you see that you get by pulling back these torsors to the third portion is that you get a scheme that is determined by some group homomorphism from the stabilizer to the underlying group of the torsor. And we can explicitly say what this homomorphism is. Like, it extends the obvious guy in the generic fiber. This obvious guy is the one that is the identity on G bigger than I and like trivial on remaining parts. But then you also need to conjugate it by something to make this work. And that something is this sort of arithmetic invariant, which we call the group theoretical difference of lambda, the co-weight of G. And I mean, this relates to the difference in algebraic number theory, because you're taking basically the difference of conjugates of uniformizers, but you're applying also the co-weight to it. The reason why this appears is when you're computing like global sections of LT, where T is the Néron model of the centralized maximal split torus, and you try to calculate OP valued points of that. Then when you try to separate factors, this sort of object is what comes up, basically. And I mean, the choice of uniformizer is not so important, because if you replace it, you just get this difference by a unit. Right. And now we need to use these objects to tell you what the specialization looks like. I mean, for that, I have to, I should say that we were tremendously inspired by a conjecture of Hipapas-Rapoport. So they conjectured that once you know the two fibers together with the G action, you should be able to recover the local model, which I guess I took it as meaning that you can recover SP. I'm not sure if that's true. We're not sure if that's true, but we can show something weaker, which is still good enough. Namely that if we include convolution and we vary all the G's and all the mu bullets, and also if we fix what SP looks like when you restrict it to this third part and its integral points, like it should be the natural projection, right? And then you can actually pinpoint more or less what SP is. You know, there's just one collection of continuous maps that satisfies this property, okay? And so the idea for that is just, I guess it uses more or less the Lassale decomposition reduced to some Galois restriction of scalars of a split group. Then you assume that you refine your sequence so that every element has simple supports. And then you show that irrational points of the flag varieties tend to integral points of the third part. And yeah, so that's what you do. But I mean, notice that this method is somewhat inexplicit, because I mean, if I gave you a point, if you gave me a point and wanted me to tell what SP is, I would have to find a bigger group, then I'd have to resolve the local model, at least partially, and I could only tell you really what SP is over there. Then you'd have to backtrack everything, which probably could be hard, especially the resolution map. Yeah, when you sum all the components coming from the convolution. So it's quite inexplicit, but it's good enough for us because we can consider the same lifts as before, which we used to compare the special fibers in FHLR. We can show that they have some functoriality. The type of functoriality that we need is like for morphisms between very restricted split groups, more or less. And also when you have a twisted group, you need to embed it in some group of this form. And that's actually where the P equals 3 no triality hypothesis comes from. Because that becomes just incredibly hard, or probably false. But it works apart from that. And also the case P is equal to 2 and all the entire groups where you can construct a lift. So excluding those cases for a moment, you can define this candidate, which I call M pre, as again the AWM flight closure of FG mu inside GRG underline OE. This is defined, beware, this is defined with power series. I mean, should probably made more clear, but yeah. And what we can show is that this object, again, by the same type of techniques, we show that this object is normal, Cohen-Macaulay, and satisfies all the desiderata. Right, and now it's time to basically compare the two. And so, sorry. The first thing is that when you compare, so first you need to compare like the two fibers and this convoluted third part. In both settings, like the FHLR setting and the AGLR setting, which is a Schultz-Weinstein point. And so with some work, you show that they are compatibly isomorphic. They're isomorphic that are equivalent and they glue in the obvious sense and so on and so forth. And then by the way we characterize the SP morphism, we also get an isomorphism of specialization triples between the FHLR side and the HLR side. So now you just have to apply fully faithfulness for this proper flat rich p-adic Kimberlitz. And this is going to tell you that the V sheaf associated to pre is equal to M G mu, the V sheaf we're interested in, which in turn implies that this hypothetical M log G mu actually exists. And it's even equal to this underline mu pre. So, I mean, not only do you get representability in general, because you can always, it's always enough to embed it in a very restricted split group in general. I mean, these lifts are only important if you want to say what the special fiber actually is. Not only do you get that, but you also get the previous theories, the previous theory based on power series that have been developed in several papers by several people, actually is actually compatible in all cases with the proposal of Schultz of Einstein, which was something that was beyond odds type data was not so clear. Like for instance, for exceptional groups, it seemed very out of reach, but this means that it must be true. Okay. So Yeah, that's it. Thank you.
Let's thank João. Any questions?
I have a question. I don't know if you can hear me. So in the
Yeah, we can.
In the Berkeley notes, I think the conjecture includes that the special fiber has to be reduced. I mean, is this
Yes,
part of
that's
your
true.
results? Exactly when does it hold? Maybe.
Yes. Yeah, I'll repeat that. Okay, so the desiderata that I mentioned, yeah, sorry, maybe that was a bit not so clever on my part, but it includes knowing what the special fiber is. So I'm claiming that once I base change this to FQ, this is equal to AG mu 10, this canonical deperfection of the mu invincible locus. Okay?
But it's
And
reduced.
so,
I mean, this includes that it's reduced, right? You're saying.
yes, because it's
Okay.
weakly normal.
Okay.
Yes, that's correct. Yeah. So it's just small assumption that you need to include, like those two cases, when p is equal to 2 and p is equal to 3, those two families. Yeah. Yeah, so this proves the conjecture. Thank you for the question.
I mean, just for clarity, I mean,
Yes.
I mean, in our paper, there's also this uniqueness conjecture as a scheme. Do you prove
Yes.
this?
You need to remind me what is the conjecture? I mean, you just said, I mean, I don't think we proved it because you said only based on, you said a scheme that has a special fiber is the right one, right?
Right.
And like the two fibers are the right one, and you know the G action. We don't actually prove this. That's what I mean. I mean, it really helped us to think about that. You know, there was a point where Schultz was doubtful that it made any sense, and but then I thought about it again. Okay, so we can't really prove it. So we need more structure. We need to add convolution. We also need to let G vary. So for instance, this includes cases of wild ramification and so on. And we also need this search data to really tell what the local model is, which means it's still very, I mean, I think it's far from your conjecture, to be honest. Because you need to show somehow that, yeah, you need to show more stuff. Like I don't really know. I mean, it still sounds complicated.
I mean, let's assume P is greater or equal to 5. I mean,
Yes, that's fine.
even in
Still, we still don't prove the conjecture in the form that you wrote it in the paper.
Okay.
Like, because we need this extra data coming from this homogeneous part.
Okay. Thanks.
Yeah. Yeah.
Any further questions?
Can I ask a very basic question?
Yeah. Sure.
So at the beginning, in one of the earlier slides, you said this association from G mu to mg mu is functorial. What do you mean by functorial?
Yeah. Okay. I mean that you should have a morphism of this type. Okay. Once you have like a homomorphism from G1 to G2, which is defined over the same ring of integers over ZP. So I'm working over ZP. Should be a ZP homomorphism at least. and it should map the co-weight, or rather the conjugacy class, if you want, to that of one to the other. If you have that, you should have a morphism of the M-locks after you extend scalars from E1 to E2, because the definition field of the first definition field is going to be smaller.
So in particular, it commutes with like products and.
Yes, it does. That's also, I mean, I wasn't claiming that, but that's also something that holds. Yeah, that's true.
And like Bay restriction as well.
Bay restriction is complicated. Like the relation, it doesn't interact so well with the local model. That's actually the problem. Very restrictive parahorics are very singular. I mean, they're very in a way lead to very ramified situations, and then your local model. I mean, it's not really. It's an interesting object. It's hard to tame. I think even for restriction of scalars of GLN, if you try this old modular approach to defining by the Kotlitz condition, I think already there you would find problems. These flatness problems, I think they might appear already at that level.
So even if mu is just concentrated in one coset, or no.
No, that case is okay. But that's sort of the truth. Yeah.
So there is some statement about restriction of scalars, right? That if you start with
Oh.
G mu over some field and then restrict G down.
Yeah. If that's what you meant, yeah. Right. Yeah. That. No, I was worried that something else. Yeah. Like I think also in the work of this is a question that in the work of Papas, Kapopop, and Smitling, like they have this introduction to local models, and they set out some properties that in the ideal world what the local model should satisfy, and I think they say that it should be somewhat functorial when you extend your ground field. Like instead of just working over ZP, you try to extend the definition field. But just using the affine Grassmannian, I don't see how to construct a morphism.
But how does your local model compare to the Papas-Rapoport Smitling? Because their models usually have
every time that they are. Yeah, every time that they are defined, they coincide. Like, I mean, you'd have to take the flat closure.
Flat closure, yeah, okay. So your models, if you restrict to the Hodge type case, you don't have any moduli description, right? Or PEO. Because it's still the flat closure model.
Yeah, I don't think you have a complete modular description in all cases. But I'm not exactly an expert. But,
okay.
In that,
thanks.
I don't think you get it.
All right, so I guess we will take a 15-minute break and